putting it. Okay, sounds good. So I'm going to present this paper, Understanding Adversarial Robustness Against On-Manifold Adversarial Examples. And I'm going to explain like what everything, like the whole background so that it's easier to follow when I do come to the paper. My name is Ehsan or Rahman Mohammed. You can reach out to me at mrhm326@uw.ca if you have any questions. And please stop me anytime if you have any questions, because it's a little bit hard to follow, or most likely not that LLM kind of paper. So that's why, in order to follow along, I think if you have any questions at any point, please let me know. So without further ado, I'll get started with what are adversarial attacks. Adversarial attacks are basically like carefully calculated, like these are ways in which carefully calculated noise is added to an image or maybe a text or any kind of data. And that noisy, like noise-filled text, image, or data would be getting misclassified or mislabeled or mispredicted by an AI model. So here, as you can see, the original image is actually of a benign nevis. And then if I have carefully calculated some adversarial noise and added a little bit of it, that means like the noise has been exaggerated just to make sure that it's visible. But then like if you scale it down to maybe say a factor of 0.04 and then add it to the image, then you'll obtain the adversarial example, which is on the right side of the slide. These two look visually the same for us as humans and even radiologists or like dermatologists in this case. But the image classification model would be misclassifying it as a malignant nevus. Not just misclassification, but the misclassification's confidence would be much higher than what we might suspect. So there are a lot of different types of attacks. I'm going to do like an attacks 101 here. The first one, most common one, is called the fast gradient sign method. As the name suggests, what we are going to do is we are going to capture the gradient of the image after it has been passed through the model. And then based off of the gradient, we are generally required to reduce the gradient, right? Like we do a gradient descent instead of gradient ascent. But in this case, we want to fool the model. So we want to increase the error. And that's why to the image, we are going to the add the gradient instead of decrease the gradient. So that's why we are getting, and we are only going to use the sign of it. So the sign of the gradient. So if the direction is like positive, then we have to go in the negative direction and vice versa. The amount of gradient that will be added or subtracted depending on which direction we are moving would be nothing but epsilon. Um, and this is like a single step perturbation in the direction of the loss of the gradient sign and not the gradient sign actually. The next one is iterative FGSM. Basically, like the second step here is, we keep doing that for multiple iterations until we exhaust like the number of iterations that we have set, or if we are able to fool that specific image. So if x subscript t plus 1 is able to fool the model and is having a label that is different from xt, then we stop it. But until then, we keep iterating the image through the model and keep finding the gradient and adding the gradient. So this is like a multi-step FGSM with a projection back onto the epsilon ball. And that's why we have the B subscript T of X. Some of the other attacks which are really helpful or which are really prominent in the literature, one of them is called the projected gradient descent. Again, here the most important step is being the projection. And then this is basically like IFGSM with some kind of random initialization, and it's also one of the strongest first order attacks, first order L infinity attacks, which means there are like multiple types of norms, right? Like L1, L2, and L infinity. So this attack is in the L infinity subspace. So that the distance, the way they measure the distance from the decision boundary is using L infinity norm. But you can also easily get an L1, which is like Manhattan distance based attack, or an attack which is based on Euclidean, which is L2 norm. So you can you can do a quick Google search and find different variations of the same attack in different norms. It's basically like, how are you calculating the distance from the decision boundary? The next one is deep fool. It's another iterative, it's an iterative attack where we try to compute the minimal perturbation. So instead of computing a perturbation which is only um, initiated or governed by the parameter alpha or epsilon in our case, we actually try to find the minimum perturbation that will be helping us in crossing the nearest linearized decision boundary. So generally decision boundaries can be very complicated, but if we want to get a linearized approximation of the decision boundary, and they do that in their algorithm, for which you can look at in their paper or a code. And then what we find is, if we are able to locate the nearest decision boundary, we first find the vector. That means the direction in which this given point has to move to go to that decision boundary, which is nothing but the one that you can see in the green. The green is nothing but the vector, and then it's being multiplied with the delta, which is the magnitude that it needs to cross that decision boundary. And all of these are calculated with uh, a specialized function which predicts, which is basically predicting the class of the xt, right? In this case. So you might have to do it various number of times, or here in our case, what we are trying to see is, if we have a given point, there can be various decision boundaries that can be around this given point, but we want to find the closest decision boundary. So fk would be representing the closest decision boundary at a given step t. And again, this can be iterative or can be a single step attack, depending on how you want to go with it. Um, and the last one I would like to touch on here is something called as Scalini-Wagner attack. This attack basically takes the L2 norm, like it's an L2 variant. That means we are using Euclidean distance from the decision boundaries to calculate our adversarial noise or adversarial attack. But here we are also trying to um, use logits instead of just the final class prediction. So we are trying to minimize the effect that it may have on the logits, because changing the logits by a lot will change the confidence by a lot. That is not something we want to do for the given class. So like xt has label of dog, for example. We don't want to change the logits of that dog while making sure that we are actually making xt as a cat, say, for example. So that's why we would be able to see that while the label is not equal to the current label that X is having, so I is not equals to the predicted label Y, we are trying to minimize the logits of those two classes, so that the logits between different classes are minimized while the error is happening. This is just a much clever type of attack, right? Like through logits, you might be able to detect, oh, this logit is very low and this logit is very high, and you will be able to say, oh, there might be probably like less likelihood or less confidence in this prediction. But Kalini Wagner wants to do something interesting by saying that the confidence of those two classes should kind of more or less be the same, not a drastic change in the original laws, while keeping all while increasing the loss of the um, predicted label. How that makes a little sense, but these are just different kinds of attacks. I'm not doing any justice by going through them only one equation at a time. You can search up any attack of interest, but there are various ways in which you can do. The most important thing that you have to remember is gradient, decision boundary, how you are varying from the decision boundary, which kind of distance are you using to calculate that distance, whether you are using the final prediction or logits or internal features in the model. that is all different choices that you can make, and it will lead to different kinds of attacks that we have seen here. Anyways, so coming to adversarial defenses, which are nothing but solutions to adversarial attacks. The first and the most common would be, and the most logical would be adversarial training, which is nothing but a data augmentation based solution. Here in adversarial training, as the name suggests, what we are trying to do is we are trying to train the
Just a
model.
second.
Oh yeah,
Uh,
sure.
I just wanted to get one thing clear. So
Yeah.
basically, the adversarial attacks is basically we want to get that particular image uh, closer to the decision boundary that the model is predicting.
Yes.
So if the image is closer to the decision boundary, given the structural, basically the visual properties of the images are the same, then the model, there's a high chance the model can misclassify that particular image as a opposite class, right? So that's
Makes
the
sense.
main idea.
Yeah. Yeah. That's the main idea. Yes, exactly.
Okay,
Um,
and basically, so you said you have listed a lot of methods. I couldn't actually understand all of them because it was
yeah.
very fast.
Yeah.
But
I know.
you actually mentioned a gradient-based approach. You said ki we actually can calculate a gradient, and instead of going into the gradient descent, we can go into the gradient ascent or something like
Yeah.
that
Mhm.
to flip the model's class. So suppose if I want to perform an adversarial attack on a particular image, so I'll have to know the properties of the model also, right? So
Yes.
the
Yes.
same adversarial attack is not necessarily meant to work on different models, right? It's only meant to work on a single model.
Yes. Okay. Yeah, that's a good question. So the adversarial example that will be generated for a given image will be model specific because you're trying to fool this model. You're going to find the gradients of this model with respect to this image that you have passed through it. And then you're going to use those gradients to fool the image, like, or change the image.
Okay, so
Um,
I'll have to know the details of the models as well.
so yeah, these are
So
white box attacks. So that's why they are like you need to know the gradients, you need to know the model, or what you can do is you can also create a gray box model, which means basically if you know that the model that is being deployed or used is, for example, ResNet, then you might go and train ResNet on a potential data set that they use to train their model, and then generate a potential adversarial attack and see how it will attack that deployed model. So,
okay, I have one question regarding this.
yes.
So suppose we have a OpenAI, for example. OpenAI doesn't reveal any of its models or the training data. It's all API based. All of its models are closed source. So
Yeah.
suppose if I want to fool the OpenAI's diffusion model,
Mhm.
then there's no proper way for me to do that, right? So why do I need to provide a solution to the adversarial attacks if I cannot access that model?
That's an interesting question, but I mean, as I just mentioned, there are gray box attacks. So if you know what is the potential data that has been used to train this model, or what is so the way, and then there are black box models, which are basically like, you pass through data, like batches of data, like input data, and you also obtain batches of output data, and then you see, like, try to see if you can come up with a mapping between the input and output, because it's not whatever they might be having behind closed doors is nothing but a probabilistic model, right? So you can try to approximate that probabilistic model using the input output pairs that you have already obtained, and that will be a white box attack. And there are a lot of white box attacks as well, but for the sake of this presentation, I'm just going to focus on white box attacks. And yeah, that's
No,
how
like basically my point was if I don't reveal the model details and keep it extremely closed source, then there's no way that they can actually
So
figure out a logical way to attack, right?
they
So
can
that's
so
still
the
attack.
there are actually black box attacks also.
Yeah.
Acha.
So there are black box attacks, but in there, I think the thing is that you have to query the model a lot and stuff, and there's a lot of ways there
Trial and
also.
error. I think trial and error
Yeah,
both works.
yeah,
Yeah. Yeah, so if you have that input output pairs, then you can most likely be able to create an approximate probabilistic model. And then using that
yeah.
model, you attack it using a white box method, and then you are able to get that whole mechanism is basically a black box setting, right? So
Okay.
yeah, you can do that querying just the way Arath mentioned.
ठीक है,
And that's why we
interesting.
need a solution, because whether or not it's a white box attack or a black box attack, it's still attackable is the fact. And that's why, and then a lot of models, there is another property that I wanted to mention later, but maybe I should mention it right now so that for the sake of clarity, and that is called adversarial transferability, which basically means if you have a model image pair and you get a variation of that image, like an adversarial example out of that image, right? Just the way I showed in the slide one. If that image is able to show fool a specific model, it also has a higher likelihood of fooling other image classification models, because all these models at the end of the day are trying to are nothing but probabilistic models, right? Like of inputs and their predictions. So there is some form of truth to everyone, irrespective of what kind of data you train them or what kind of task you train them on. So there is this adversarial transferability characteristic, which is basically if I have obtained an adversarial example on a given model, I can also, like, there is high likelihood that I can also fool another model which might or might not be doing the same task or might not have been used with the trained with the exact same data set. So you can also search up that concept of adversarial transferability and black box attacks. Um, okay. Yeah. So moving forward, adversarial training, as the name suggests, what we are going to basically do is, we are going to train the model on adversarially perturbed samples, which is nothing but adversarial samples or adversarial examples, to make the classifier inherently robust. So what we do is, for all the possible images in the training data, we create like a bunch of adversarial examples out of those models, just the way I showed in the slide one. You pass the first image as a benign Nevis, then the adversarial image also as the having the class label as benign Nevis, and then you train the model. So that way, the model is trying to be able to learn that, oh, I should not just be looking at this, but a little space further from the data manifold, so to say. I went
Yeah,
a little.
one question.
Yeah.
So suppose I train a model with this data augmentation strategy.
Yeah.
So the model, suppose like I have two models, one without data augmentation and one with data augmentation.
Mhm.
So most likely the decision boundary will be different across these two models, right?
Absolutely. Yep.
So the main idea of the adversarial attacks is that how can I move that particular image closer to the decision boundary to confuse the model, right? But I
Yes.
can still do that for this augmented model, right? In theory.
Yes, you can, but you are trying to limit your space and you are trying to push the decision boundary further away. So remember the attack parameter epsilon. So we are trying to bound the amount of distance we can travel from the original data point towards the decision boundary by only epsilon. So if
Okay.
the decision boundary is within epsilon, you are able to jump past it, you are close to it, or you are on it. But if what we are trying to do with adversarial training or any of the defenses is possibly to push the decision boundary further away from that epsilon parameter, such that even if there is variation in the data point, it's not able to cross through it. Because if you have a high epsilon value, you're probably going to change the image so much that it is a recognizable change, or it's a change that can be caught, right? Like if there is some kind of, like if there is a human in the loop, then that is going to happen. But then, yeah, you're just opening a different can of worms altogether. But yeah, you're right. But the scope of that attack lowers. It's not going to become completely foolproof.
Yeah,
uh,
it makes sense. Yeah.
yeah.
Okay, got
For
it.
example, if you are having epsilon of 1e minus 3, and you have completely trained your model with adversarial examples which are having epsilon of 1e minus 3, and then you attack that same model with like 1e minus 2 or 1e minus 1, then most likely, yeah, you will get bad results, right? Like you will be able to fool the model. So it depends on the kind of epsilon you're selecting while doing adversarial training. and the kind of epsilon that you think would realistically happen in a real world setting, given that at some places there will be human in the loop, at some other places there might not be human in the loop, and how do you, like, which battles do you pick and choose? So, but that's a good question. Yeah. Okay. Moving on, there are a lot more adversarial attacks that I just wanted to discuss. Some of them, as we can understand, are based on regularization. So there is gradient regularization, which basically means that, oh, penalize like large input gradients. If you have some images that are going to change the gradients of the model by a lot, then try to clip them. There is something called as Lipschitz regularization, which is another topic altogether. So I'm not going to go into that, but I'm just going to share this with you that you can try to enforce Lipschitz constants, and Lipschitz constants are basically constants which try to assess or find the ratio between change in output versus change in input. So it's a ratio between uh, the difference between outputs versus difference between inputs. We want to minimize it as much as possible. So that's why we want to bound the Lipschitz constants of our neural networks, and that is a very good and strong adversarial defense. The other one is like manifold regularization, and we will be looking into manifold regularization. That's why I have just highlighted it here. It tries to encourage images to move towards the natural data manifold under perturbations instead of, there will be an inherent structure to lay the model, right, to the data. So we want to stay within that original or natural manifold versus having decision boundaries which are like going crisscross or across that data manifold. So manifold regularization is another one which is complicated. There is label smoothing, which we all use as regularization, but it's not
I'm
just good
sorry, I
for.
think we lost you in between. Can you please repeat?
Oh, okay.
Yeah,
Where did you
there's
lose?
some missing.
You can start with the feature scattering and manifold
Okay, sounds good. So feature scattering or manifold regularization, I think I've highlighted it because we'll be looking on data manifolds today. So what basically feature scattering or manifold regularization does is, if we generally a given set of data has a natural manifold to it based on semantic similarities between those data points, right? Now, what we want to do with the decision boundary is we want to make sure that the decision boundary understands semantics instead of understanding like some irregularities, right? So that's what basically manifold regularization would do, for which you need to, at every step while you're training, you want to find the embeddings or find the manifold and then find the distance between the decision boundary and the manifold and then use that as regularization. So that's basically what's happening, but something that you can keep at the back of your head. Next one is label smoothing. Label smoothing is something that we have all used as regularization to avoid overfitting. And this also works for adversarial robustness. There is one more which is called trades. Basically, as the name suggests, it's a trade-off between natural accuracy and robust accuracy via KL divergence. So it uses KL divergence to, make sure that there is a slight decrease in the natural accuracy while the robustness accuracy is increased. How do I manipulate that, or how do I keep that trade-off in check? So it tries to optimize that trade-off. Another few set of ones are like structural, such as like random smoothing or ensembles. Ensembles is one of the easiest one, especially like we have a lot of models such as like ML models such as decision trees, right? And we know how we can avoid overfitting in decision trees is by creating a random forest. So the same concept can be applied here. Instead of having one specific or one single model giving us all of our predictions, we can train multiple set of models with multiple initializations, different subsets of data sets to different extents and all of that, and then get an ensemble or majority vote. Input transformations, pretty simple stuff. Like if you apply pre-processing such as JPEG compression, bit depth reduction, and a lot of other things before passing your image into the model, you might be able to eliminate the adversarial noise that has been applied to it. Okay. There is defensive distillation as well, and path-specific defenses that you can look at. I'm just going to skip past through them. I'm probably going to go to data manifold from here. Um, so now coming to data manifold, because that's a central concept to this paper. What we have, we know what data manifold looks like, right? Like it's a low dimensional structured surface which is embedded in a very high dimensional space where the natural data lies. So if you have an image of 224 cross 224, then your dimension is, I don't know, whatever is the product of those two values, right? So that's a very high dimensional space. But for the sake of maybe visualization or for the sake of dimensions that really matter to us, because not every pixel is worth looking at, right? So that's why we generally look at a low dimensional manifold or low dimensional embedding, and that is nothing but a data manifold. Some of the intuition based off of that is generally when you have data on the data manifold or closer to the data manifold, then it's most likely closer, closely resembles the original data. So the intuition is that any off-manifold regions will be corresponding to maybe unnatural data, adversarial samples, or off distribution, like out of distribution samples. Some more intuition is that although images would live in the data manifold, their valid configurations generally form something like a Swiss roll surface, which you can see over here, right? Like a manifold can actually be folded into itself. So if you have A or B or C or D as well, as you can see, like within A, you do have that manifold which is highlighted in the red belonging to a given class, and then it gradually goes and merges into a different kind of class, but there is continuity in the manifold itself. But as you can see, if you move on the data manifold, you might be actually leading to adversarial attacks. Also, while you're moving normal to the data manifold, you can be leading to adversarial examples, right? Like if you move above, like in the direction perpendicular to the red manifold, or go below, you will land into the light blue class. So some of these manifolds have these specialized structures where they are like Swiss roll surfaces, uh, instead of like more like the C or D. I don't know why the C or D is not showing up there. But okay, any questions on this one? I mean, folks do
Yeah,
understand what data
just one.
manifold are.
Data manifold is basically to identify how the data in a high dimensional space may look like, right? Something like
Yeah,
that.
yeah,
It's a projection.
it's a
Uh,
projection, yes.
wow, what is the reason of this Swiss roll? Can you explain again? I couldn't actually understand it. So
Oh,
if it's
this
a
is just to
projection,
give like a little bit of more intuition into things. The Swiss roll surface, some of the manifolds, not all manifolds, but there are some manifolds which uh, may actually look like this.
mhm,
So they are actually high dimensional, but I mean, they are uh,
overlapping some. Yeah.
overlapping on each other. So you might assume that the image is not doing justice because it has to be represented in 3D, right? If we rotate this manifold here, we might
Mhm,
assume that if you are looking at from the axis from the top, you might assume that anything behind it is actually being clustered all as red class instead
mhm,
of, as some other classes. But then you might not be able to, and then you also see that the slight variation that is happening between the red and the yellow, or the orange, you might assume those two are very similar classes, so they might not have any classes in between, which are very unlikely or very different from like the orange and red kind of represents like cat and dog, both being animals, both belonging to the concept animal, but the blue maybe belonging to a concept. I'm just giving examples, right? Like, I don't know, a
Yeah,
tree.
so
Maybe.
is it just for better interpretability of the data, like just converting into the low dimensional space?
Yeah, the reason why you want to look at the lower
Mm-hmm.
dimensional embeddings is
Yeah.
because you want to either visualize it into the 2D, like the way we do using principal
Yeah.
component analysis
Okay.
or linear discriminant analysis or whatever. The other reason is because
Mm-hmm.
a lot of these dimensions, right? Like if we treat each pixel as a dimension in a 224 cross 224 image, then
Yeah.
what we are basically looking at is like these huge number of dimensions. But not all of
Mm.
those dimensions have anything to do with the final
Yeah.
prediction, right? Most of
Yeah.
those dimensions are useless. So as
Mm-hmm.
we move through the model, we are actually doing a dimensionality reduction. So we
Mm.
might be selecting some specific embedding from an intermediary layer, which has like
Yeah.
a dimension size of 100. And though only those 100 dimensions are very important.
Mm-hmm.
Uh, and we have gone from pixels to
Mm.
blobs to shapes to now objects, maybe. So we are probably like looking at objects or space or something between there and not at all pixels. So that's why
Yeah.
looking at
Yeah.
it.
Okay. Got it.
I hope that was helpful. I'm not able to do justice
Yeah.
with the
Yeah.
3D
No, that's
visualization
good enough.
because it's really hard to explain 2D concepts on 3D. Sorry, vice versa, I believe. Okay. Anyways, coming to data generation, I'm going to be quick with this one. I hope everyone knows what data generation models are. Basically, you know that every data is actually coming from an underlying distribution, which is P subscript data of X. And we can basically sample new samples from or new realistic points from that sample, even though we have not looked at them before. The way it happens is we draw like a latent vector, um, um, say for example, from a Gaussian distribution, a mixture of Gaussian distribution, I don't know, whatever distribution of your choice, and then we use a neural generator. If people have worked with autoencoders or something like that, you know what encoder decoders or generators would look like. So z of t z comma theta is nothing but to map these latent variables to back to the data space. That means it's doing sorry, which one is it doing? The first step is the encoding. The second step is the decoding. And then sometimes this decoding will likely take the form of a GAN or of a variational autoencoder or a diffusion-based model. Sometimes there is an additional thing that you want to do on top of that is to denoise samples, because sometimes these reconstruction-based samples or data generate like synthetic data that has been generated is pretty noisy. And then there are some learned some score functions that are able to give you how much noise is in there, and then you can use those score functions to improve the data generation quality. But most likely you're only going to look at the first two things. You're actually extracting a latent vector, which in our case is going to be a vector from the low dimensional data manifold that we have, and then we are going to map it back to its image representation, which is the second step. The third step is the third bullet point is basically how do we find that data, and the fourth step is basically to improve the quality. Not very necessary. I hope there are no questions on that one. So here in this paper, they are looking at two different types of adversarial examples. The reason why I mentioned PGD, FGSM, fast gradient sign method, iterative fast gradient sign method was because they are all traditional adversarial attacks. Here in this paper, they have specifically introduced two types of generative adversarial attacks. The first one is generative adversarial attack. Um, Basically, all the steps are taking in sample, taking in a generative model, using that generative model. So you might go back and look at PGD and how like this is very similar to PGD, and we are doing the projection on our space. We are making sure that the z dash and the z are within an epsilon bound, so they are not like very different from one another. But as you can see, we are doing the gradient calculation on the generative model instead of on the sample. If you go back and recall what we were having in PGD, we had X here, but instead of X, we are having the generative model. So unlike FGSM or PGD, which was working on the actual image, we are actually applying PGD or FGSM on the latent space. That's just for us to do that's just for us not to attack the original image, but to attack the low dimensional space to see how that attack on low dimensional space eventually translates into high dimensional space. Is that
So
clear?
one question. So if I'm attacking the latent space,
Yes.
does that necessarily mean that the decoded version of that particular latent space will be that image will be similar to or visually equal to the image that I hadn't attacked before? So I'll have two images, right?
Oh,
One with attacked and one
yes.
with attacked.
Semantic similarity with the original image, right? Yeah, that has to be assured, right? Because the task of the generative model is to do that mapping. So once you have learned a generative model, like in an autoencoder or a variational autoencoder or whatever, you know that that mapping is going to happen. It depends on your reconstruction laws, but
Okay,
that
so the
we are
model
assuming
is
that it's happening. Yeah.
model is trained in such a way that if I'm attacking a latent space, then that generation should match with the ground truth image, something like that.
With the semantics of the ground truth image may not be exactly the same image. Most likely will be the same image with what couple of variations will be coming from
Uh,
it. Yeah.
like if I'm using GANs, so GANs are very unstable, right? So they are not actually very popular. The training is very unstable, so they actually lead to very blurry image generations usually.
Yeah.
So is it like this is like, I don't think this is a good way to go, right? I think the diffusion process would be the best way to go from here. That's what I think. Like what
Yeah.
you.
But yeah, I mean, but they're trying to do yeah, you're right about that's why I just wanted to mention that the quality can be poor. There can be a lot of instability. They can be stuck in I don't know, local minima or whatever of that sort, right? So yeah, you're right about that. Uh, they could have used diffusion models, but they are using GANs and variational autoencoders, if I'm not wrong. The reason behind them doing that, what I think is they just want to explore the concept of the data manifold instead of going too deep into the image quality. Um, and the other reason might be diffusion models can be expensive. GANs can be expensive as well, but yeah,
No,
I'm
GANs
not.
are more expensive. GAN maintain two models, right? Diffusion is very simple.
Yeah, so maybe they will be doing it in the next.
But yeah, diffusion model doesn't have any latent space. So I don't know how they
That's the
will.
reason. Yeah, that's the reason. Yeah, that's the reason they just want to attack the data manifold instead of attacking the image. So instead of doing denoising or diffusion, as in the diffusion model's case, they want to attack the low dimensional manifold, uh, like the data manifold, and see how that attack way translates into the original um, like output. So yeah.
You said that they don't have a latent space. So why do they not have a latent space? You're starting from a noisy image, right? You're sampling from a distribution. That itself is the latent. Can you consider that as a latent
No,
space?
no, latent space इसलिए नहीं है वो क्योंकि the dimension of that is exactly equal to the image. वो it's an image to image generator model. हो सकता है बीच में latent space हो, but it basically it runs for 1,000 steps, sequential steps. It generates an
Mm-hmm.
image at each iteration and उसी को वापस feedback loop में करता रहता है generate धीरे 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 धीरे. It's basically a denoising network. It removes the noise from the image. So
Okay.
could be considered as a latent space, but I think जो जितने भी current models हैं वो vision transformers पे based हैं. So vision transformers में तो of course latent space अभी तो concept में ख्याल तो है नहीं. Maybe हो सकता है आ जाए कुछ, but I don't know. अभी तक तो मैंने नहीं पढ़ा. जब जितना मैंने पढ़ा था diffusion models में उसमें ऐसा कुछ mention था नहीं.
Mhm. Okay, so in this example also, in GANs, you are saying that so where are you applying the data manifold thing here
Okay.
in the latent? So in the latent space are you also learning the latent space so that you know?
Okay.
Uh,
That's a good question. Yep. Absolutely. So they have they have trained the conditional GAN and the conditional VAE to do the image generation. Once they are done with that, now what they are doing is, instead of attacking the first like the image in the image right off the bat while it is being passed, they are only attacking, or they are doing the PGD attack or FGSM attack on the latent space. Does that make
Okay, so in conditional GANs and all, I don't remember actually what they were, but you are saying that they conditional GAN actually makes a data manifold in the representation space,
No,
right?
I was just trying to draw a parallel between latent space and data manifold, given that latent space is nothing but a low dimensional representation of that image, right? The image that has been encoded, that the latent space is going to be a low dimensional representation. The latent space representation is going to be a low dimensional representation of that very original image. So, and that has been assumed to be where they are trying to look at their data manifold. So their data manifold definitely would not be looking like images, right? Because that is like a very high dimensional data manifold. They're only looking at latent space, and they're also varying latent space dimensions. We'll come to that like eventually. But
Okay,
here
okay,
they
okay.
have learned a conditional GAN. Conditional GAN basically is like, you don't just generate a random image, you generate a random synthetic image, but you generate an image which is similar to the image that we have. So
Okay.
you can pass a prompt, or you can pass an image, and you ask it to generate a synthetic image. It can give you a synthetic image of the same class, but with a lot of variants. The conditional here is that the pixel to pixel difference should be the same, should be the minimum. And that's why you're trying to generate images which are as close as possible to the original image, because that is our
Okay.
concept behind attacking, right? So that's the condition. But again, conditional GANs would mean whatever you want to condition it upon. Nothing complicated there. So,
Yeah.
okay.
Okay,
I
okay,
hope
okay.
that.
Got it,
Yeah.
got it.
And
Thank
we are
you.
not attacking the initial image like in PGD, where XT is representing. I can go back to that slide real quick. Oops. Okay. What am I doing? So even if we assume FGSM, we have X and we have f of X. So that means we are attacking the image X. But in our case, in this case, we are actually attacking the latent space, which is Z, and the G of Z. That means f of X. F of X is G of Z here.
Okay, so that's the major difference between both the traditional one and this new
Yes.
generative.
Yeah.
Okay.
Okay. So next thing, again, similar, a little more mathematical concept. I'm of course not going to go into eigenvalue decomposition, but they have also created this thing called eigenspace adversarial attack. And in eigenspace adversarial attack, what they are trying to do is, um, we have, again, comparing it with this, we have zt and g of z, z subscript t. Here we have delta zt and f of x plus delta zt projected on ay. So what is a sub sorry a sub y? A sub y is the eigenspace. I think people know what eigenspace vectors or eigenvalue decomposition looks like. So if I have a huge space for a given image, and I find the eigenvalues and eigenvectors, I'm basically trying to find vectors in which the maximum variance is going to occur. The vectors in which maximum variance is going to occur are going to be my top eigenvectors in this eigenmatrix, and the top or bottom eigenvectors are going to be those axes or those vectors or directions in which the variance is minimum.
Just a
Okay.
question. So
Yeah.
the eigenvalues of these vectors must be very small, right? Very close to zero to make the image as similar to the original image. Right? If you have a very large eigenvalue, you can actually scale. I think you can actually change the image by a lot. Maybe the variance could increase or something like that.
No, actually, yeah, I should have explained this a little differently now. I understand. So basically, you have X, Y, and Z.
Mhm.
I'm going to give an example, maybe. So, maybe a simple example. Okay, not an image example. For example, we have three dimensions, X, Y, and Z. And we have, is the person hungry? Does the person have money? What's their shirt color? The prediction that we have to do is, are they going to eat? Which of these three axes, like, is the least relevant?
The color of the shirt.
So the color of the shirt is going to have the minimum variance with respect to our final, what is this called?
Okay.
Whatever, right? So that is the one. So that axis is like, if I do an eigenvalue decomposition on this huge space and that huge data, sample, then what I'm going to get is I'm going to get an eigenvector which corresponds to this axis of what is their shirt color, which is having minimum value. So that means the variation of the data within that axis is the minimum. Whereas for X and Y, which is, are they hungry? Do they have money? Will have whatever variance, I don't know. But they are going to explain more amount of data in this space. So
Okay.
yeah, does that make sense?
Yeah, yeah.
You just need to give, like, do a refresher on eigen value
Yeah.
decomposition, then it will make
बहुत time हो गया था पढ़े हुए.
So it's like doing PCA, right? PCA where you also
uh,
calculate the same thing and you get eigenvectors and eigenvalues and select the top
and select the
eigenvectors
top.
out of
Yeah,
there.
exactly.
So
Yeah.
so and according to I think what we'll be doing in this one is just varying on the top eigenvectors where variance is high, so that it remains in the data distribution somewhere when you're doing some adversarial stuff there.
Good question.
Is that what's happening?
We will come to that. I think you're just
Okay.
a little ahead. But the only thing that I want you to see right now is the eigenvalues for some of these eigenvectors is going to be huge. That means those eigenvectors, so it's basically y is equals to mx plus, like, m1 into x1
Mm-hmm.
plus m2 into x2. M1, m2 are nothing but eigenvalues. X1 and x2 are eigenvectors.
Mm-hmm.
So in our case, whether they were what shirt color they had, that m3 is having value 0, so we can ignore it. But the thing that I want you to just see for this slide is we are projecting our latent variable onto that eigen vector, or into that eigenspace. Just remember
Okay.
that, okay? And we'll come to it. Is that okay?
Okay.
Yeah.
Sounds good. Okay. Yeah. So the first set of experiments is going to be, uh, they are having a conditional GAN and VAE, as I just mentioned, which are going to be generative models, and they are going to craft on-manifold adversarial examples by perturbing in latent space using on-manifold directions. That's a mouthful, and that's why we were actually jumping a little ahead while I was actually describing it. So using these conditional GANs or VAs, because these conditional GANs and VAs are having latent spaces, these latent space representations are nothing but on manifold, right? Like they are data manifolds. They are like, as you remember in the definition of the data manifold, I can go back here. It's nothing but a low dimensional embedding of a high dimensional data. So when I'm here, I'm doing the exact same thing. It's a low dimensional embedding, which is latent space. And using this latent space, I'm going to calculate or find my adversarial examples using this one, because this is not using x, it is using g of z and z instead of x. And z being the, where is z? Z being whatever, right? Z being the
Latent
latent,
space.
yeah, representation. Or oops, okay, I'm jumping further. No, okay. Oh, uh, okay. So one question or logical question that will arise is, how do they find these on manifold directions, right? Like, how do they know that? And I think we have kind of covered that, but which is nothing but the eigenvalues of that latent space are going to show me, and that's why they have done this next attack, right? For this latent space, I'm going to project it on the eigenspace to see, to identify which directions are the most prominent, less prominent, depending on the eigenvalues in the eigenvalue matrix. Makes sense. Compared, and then they finally compared regular adversarial examples, which are created using FGSM PGD, with the generative adversarial examples, which is what they are calling GFGSM and GPGD. Wow. Okay, and they are computing all these on these data sets, MNIST, CIFAR10, ImageNet, and they have also tested it on standard models as well as on the adversarially trained models, because one thing that I forgot to mention while I was discussing the defenses is that adversarial training is actually kind of the state of the art way to make models robust, which is funny. Anyways, I know I did not do the best part with this kind of visual animations here, but bear with me. So this is a huge table, and I don't like huge tables, so I'm just going to strike off these things. The clean accuracies are not important, so don't look at these. Let us look at one, like few specific things. PGD80 is basically uh, adversarial training that happened using PGD. Okay. So as you can see, if I do PGD attack on MNIST, and if the model has been trained on standard training, that is normal training, only on clean images, not on adversarial images, the adversarial, like the test accuracy is pretty low. If I do PGD training, PGD adversarial training, and then PGD attack, then it is very high, right? That means the adversarial training is working. GPDG not working so well. Joint PGD is working. I'll come back to joint, but probably not very important, so we can skip past that. Another thing that I want to see is, yeah, that one. Another thing that you can see is PGD adversarial training also has some form of robustness to FGSM attack. The reason behind that is because FGSM is a single iteration attack, whereas IFGSM is multiple iteration. PGD is multiple iteration with a projection step. There are very amazing visualizations which you can find online to find the difference between IFGSM and PGD, which will help you explain this concept further. But I'm not going to go into that. The next two things are GPDG. GPDG is having not good accuracy on this one, which is funny and interesting. Why that is happening, you can ask the authors, or I can give you a speculative answer. But the GPGD adversarial training is giving very good results on GPD attack, obviously. But it's also giving good on GFGSM because the same pattern is repeated there, right? So that same pattern, that is the concept I was alluding to earlier, which is adversarial transferability across attacks. So not only can adversarial examples on a given data set on a given attack or model can be used in another setting, but the adversarial robustness that you obtain from a given adversarial training can also be used elsewhere. Again, another interesting thing that you can see is the PGD adversarial training actually improves this thing, but on GPDG attack, it goes variably wrong. So that means there is something that is happening in the low dimensions. So if you're attacking low dimensions, or the low dimensional manifold, data manifold, then it's probably leading to like a better kind of adversarial attack than if you're attacking on the original dimensions. So anyways, similar trends that you can see elsewhere. I'm not going to go through that, but I'm going to stay here for a little while if you have questions. I know that's
Yeah. So, I wanted to they're using FGSM attack, PGD attack, and so these all attacks work on from my understanding they work on, let's say, classification tasks, right?
Yeah,
when
we
you
are doing on
are
class.
classifying something.
Yeah.
And the one that you were explaining in, so you have some latent representation. So
Mhm.
is it like your first encoding the it's like an autoencoder. First you encode your image into the latent space, and then you from the latent space you are doing some form of classification task, and this is what their accuracy is coming out to be. Is it something like
Ye-
that?
Yes, that is correct.
And they are actually modifying the latent space there.
Representation there. Yeah,
Yeah.
exactly. Of the image. Correct. Yeah.
Okay. Okay.
Yeah. Any other questions? I know that's a huge table, so I'm like, hey, I'll probably.
Also, can you go back to the algorithm?
Which one? The
Um, yeah, I think, yeah, this one. S-
or this one?
The the next
This
one.
is the one that I'm looking at for our results, but we will be looking at the results from here in the next slides.
Ah, okay.
Haven't discussed that
Okay,
yet.
okay, okay.
Yeah, that thing still remains.
Okay. So,
Um,
so I just wanted to ask here, like the eigenspace AY, is it a selection of the eigenvectors? Is it
Good question.
some form of
Good
selection?
question. Good question. I'll come to that.
Okay. Okay, okay.
Any other questions on the table though, before I move? Okay. So some things that we have just observed, just a reiteration because it's a huge table. The first one is adversarial accuracy is greater than test accuracy. Um, did someone find that? Can someone find that for me? Would be happy if someone would be able to find it.
Can you repeat? I couldn't actually
Oh
understand.
yeah, sure. I'm so sorry. Adversarial accuracy. Okay, adversarial accuracy in this case would mean test accuracy. Did you find any place that the test accuracy is actually greater than the clean test accuracy? And I'm going to go back to the table. I've already highlighted it, so I'm going to give it away.
Yeah,
So
so the
it is,
bold ones, right, in the clean
yeah,
data.
yeah. Here,
Whereas GFGSM attack.
yeah, you are
Like a giant
actually
trial.
getting,
Mm-hmm.
yeah, yeah. You're actually getting, I'm so sorry, I'm like speaking with everyone here. 98.63 versus 99.66 and 98.45, 99.27. That is an absurd artifact of adversarial training in some cases. That means adversarial training has worked so well that it has actually improved the test accuracy. So the accuracy on clean images. So the decision boundary is now able to also become, yeah. So um, I just wanted to show that there are trends of improved adversarial accuracy that continues across, which is called adversarial transferability. So here it is 96, here it is 95, here it is 99.66, here it is 96.78. This one is higher than this one because FGSM is easier than PGD, but they are kind of essentially doing the same kind of attack. Um, Next one is sorry, what is it? Regular adversarial training cannot generalize to on-manifold attacks. Oh God, I think even I'm forgetting that. Regular adversarial training cannot generalize to on-manifold. Oh yeah, this one. Uh, Regular cannot. Yeah, so this one, like, why is it super low, right? Like PGD adversarial training, if I have done that adversarial training, then why is it not able to like
Mhm.
do well on these on manifold attacks? What's going on, right? Because you might assume that the latent space is nothing but a very refined version of the initial space where we were attacking, the input space. So what in this space transformation led to this sudden decrease in accuracy, even with adversarial training? Any guesses? I don't have many guesses, but I just have speculations. But something that you can take away from it. And we'll come to that in a bit. Don't worry about that as well. The joint PGT adversarial training observations, I don't think I have many. Yeah, I do have some of them. So here you can see that the joint probability is actually giving joint PGD adversarial training is actually giving good accuracy on all of them. Even though the joint PGD adversarial training is actually using both PGD and GPDG together. So that is another observation that we can keep in mind, which basically means that GPDG is better in some cases. And if I combine GPDG with this one, this is actually a little lower, like not in this case, but in this case and in this case. In these two cases, it is higher, which is again interesting. So there is a specific variation that comes with data set and model, which is obvious in like deep learning settings. So those are some of the observations that we just had. The coming next to the eigenspace one, as I was just talking about. So we are trying to approximate the data manifold using PC eigenspaces, just the way Arath mentioned a little earlier. I'm not going to go into what PCA is. PCA is principal component analysis. You can find what are eigenvalues and eigenvectors. Like I love 3 blue, 1 brown. So one of the best resources that I might have is to just go over there and um, watch that video, and that very helpful for linear algebra. So now what they are doing in eigenspace attack, and I'm going to jump back to that slide where I explained the eigen attack. So they're crafting the crafted attacks which are restricted only to the top eigenvector directions and to the bottom eigenvector directions. So top eigenvector directions obviously would mean on manifold, bottom would mean off manifold. Why would they? Why or how are we assuming that? Anyone has any thoughts?
So the top eigenvectors would mean like the data is in, like it varies in that direction a lot.
Yeah,
So that would mean that this direction is on the manifold.
yeah, exactly.
And when it is like the bottom eigenvectors, there is no data there. So there is no data variation there. So if you go in that direction, that would be off manifold.
That's about right. Yeah, same thing. So if we come to here, as you can see in this one, uh, there is variation along this, but there is not much variation along this, right? Like on top of bottom. Again, okay. So yeah, pretty intuitive. I'm not going to go into depth of that. So that's what they are doing. All right, like, and they've only tested on CIFAR 10 and CIFAR 100 on some wide ResNet models. What were they able to find? I was too lazy to remove the shadow, so don't worry about the shadow. You're not being delusional. So what they were able to find here is for CIFAR 10 and CIFAR 100, this is standard training and this is adversarial training, standard and adversarial. Coming back to here, the way eigenspaces are actually being manipulated is when they are selecting top eigenvectors, they are making all the bottom eigenvectors as 0. And when they're selecting or varying it only along the bottom eigenvalues, then they're making all the top eigenvectors as values as zeros. So those vectors and those vectors or in those spaces, there is no data or variation that is happening while generation is taking place. Does that make sense? Okay.
Yes.
Cool.
Have they provided a number of how many eigenvectors they consider as top
Yeah,
and bottom?
exactly. Yeah. So they have it in here. I think they have varied it as well. I'm not able to recall. I think it was 10, I believe. But here you can see that the subspace. So here they are selecting. Oh my God. Okay. Here, what am I saying? Here they are selecting bottom 500 eigenvectors, then bottom 1000, bottom 1500, bottom 2000, and all of that. So they are varying the number of eigenvectors they are selecting as well as they are moving along. And then the drop in test accuracy as they are selecting that and doing that attack on the
Okay. So
that.
the reason that they both converge to the same value is basically they could be selecting the same vectors, right?
Yeah,
After a
yeah.
certain point.
After a certain point, yes, yeah.
Okay.
Yeah, I'm not able to recall that dimensionality, but most likely that is something that is happening. Uh,
Okay. Yeah, in adversarial training, we can't say they're merging. Like, is there?
exactly. Thanks for
Mhm.
pointing that out, Aditi.
Mhm.
So most likely it is greater than 3000, or
Okay.
maybe it is a little bit of that, but
Mhm.
it's interesting to see that
That
they're
makes
merging
sense.
here,
Yeah.
but they're
Okay.
not merging here. Yeah.
Mhm.
Mhm. Again, the variation that we already saw, test accuracy is pretty low when it is standard training. Adversarial training, because it's an adversarial defense or a solution to adversarial attack, it has pretty high accuracy. Same thing here, same thing here. They are merging, they're not merging until about the end. Number of eigenvectors they are selecting while doing those attacks and projections is all given by 500 to 3000. Is that clear?
So
Yeah.
why the
Well,
bottom eigenvector always outperform the top eigenvector? So any reason for that? I thought that reverse होना चाहिए, like it should be reversed. Why the bottom is better than top?
Good question. Yeah. Arad, did you have the same question?
exactly. Like
Okay.
I was thinking if you're going off manifold, you should be able to fool the model very fast.
I love that.
दिमाग पढ़ लिया आरत का मैंने.
So, yeah, you wanted to add something to that question?
No, no, no. That was my only question.
Good question. So, let us go back here. Again, I can't do justice to a 3D space thingy. So, here, parallel, yeah, I mean, you will be able to understand what parallel and
Hmm.
perpendicular would mean, right?
Yeah.
Parallel or along the data manifold, we have, let us assume, um, two, oh my God, two dimensions, right? X and Y. Can you see my cursor at all in the thing?
Yeah. Yeah. Yeah.
So this one is X and this one is Y. I know it has a curve, so let us disregard the curve. X, Y, and this is Z.
Mhm.
X and Y are top eigenvectors or bottom eigenvectors?
X and Y would be top, right?
Depends on the eigenvalue, right?
Uh,
No, but your intuition, what does your intuition say?
That should be top
Okay.
eigen.
And this one will be bottom.
Yeah.
So
Okay.
if I vary it along these directions, I'm still in that same space of the
Yep.
so this red class is say cats.
Mhm.
So if I vary
Hmm.
like this, or if I vary like that, I'm still in classes. But if I vary like this, even by a bit, there is space here, but they're most likely in a very high dimensional space. Your data is very crowded, just like in here, right? Like if you, chalo, yeah, sorry, they are not doing justice. But if you go a little lower, you're actually jumping classes. Whereas
Hmm.
if you're going top eigenvectors alongside top eigenvectors, you're still in the same class.
Hmm.
That is clear.
Yeah.
Oh,
And now you should be able to answer your own question.
yeah. Okay. So is it like more variation which is making the sense over here? Like as you
Yes.
said.
Yeah.
So
So,
the job is to fool the model,
Mhm.
right? Using
yes.
Yeah.
this attack. And so
Mhm.
when you are in this image when it says bottom eigenvector subspace,
Mhm.
so you are actually working with the bottom eigenvectors and you are modifying the representations in the representation space using the projection on the bottom eigenvectors,
Mhm.
right?
Yeah.
Yeah.
So if you are using bottom eigenvectors, then you are actually moving off manifold and jumping classes,
Mhm. Mhm.
right?
Okay.
And so
Oh,
that was my reasoning why it should be
I get what you mean. I get what
it should fool better. Yeah.
it should full better for the bottom, and that's why it should have lower accuracy
Mm.
when compared to the top one.
Yeah.
Yeah.
Yeah, I think even I have the same question. They are having they did not have a clear-cut explanation of that, but we will come back to it on something called as excessive risk, which I don't know a lot of theory or math about, but that is exactly the question that I had, and I don't know the answer, but I kind of speculate that there might be some kind of an overfitting along the decision boundary. So. Uh, Okay, they did explain that. They did explain that using, I think it's probably, I don't know which one it is, but they're probably explaining it with D. Here, I don't know why that label has gone, but it's D. So if you see like, I mistook it as A, I believe. Yeah. Okay, so if you see here, some sample here, if you vary it along these X and Y, they're most likely going to be coming into a different class because there is a lot of variation
Mm-hmm.
along that same class. So it depends on the manifold that we are looking at. So most likely it's not looking like a manifold A, but it's looking like manifold D, where there is a lot of variation within X and Y as you move along. Whereas there is a lot of distance between uh, these two, like this one is dark red and lighter red. Whereas if you try to go into the perpendicular directions, you have to cross a larger boundary to get to some different class. So that is the most likely explanation that they are giving. Uh, it's very contextualized and data manifold specific, but I get what you mean. I also speculate the fact that most likely our decision boundaries are overfitting in a different sense because we always look at overfitting only with clear images, but we might not be looking at overfitting with adversarial images. So I kind of speculate that, oh God, where am I? I kind of speculate that there is a lot of overfitting given that the decision boundary is like not a straight line between dark blue and light blue or dark red and light red. It's more nuanced and more curvy, and that's why it's more likely to happen. Or maybe it is having a Swiss roll within itself, right? Like there is a red, and then the red goes like that, and then another red, another red, another red. I don't know what's
Mm-hmm.
happening. Like, that red is like a Swiss roll.
Yeah. Okay. So the Swiss roll is just like, just for an example, the data manifold can look like
Can look
anything.
like can look like that. Yeah.
And yeah, so we are not enforcing any kind of a structure on the latent space,
We are
but
not enforcing. Yeah, we are just trying to represent the latent space.
mm-hmm.
Uh, yeah, based on like assuming that it is not like it.
Yeah, so it's not necessary the off manifold direction will yield a different class very soon. Yeah.
Yeah, so there can be different. Yeah, exactly. The off manifold direction may have to traverse a lot greater than the
Mm-hmm.
epsilon that we are assuming to get to another manifold. Epsilon can play a role. The other role that it can play is it might have that same Swiss roll pattern, but that Swiss roll pattern can have, like with red, there is another very close shade of red going alongside it, and then a little
Mm-hmm.
further away there is a blue. So that's why the light red jumping to low red is closer than the off manifold direction, which is blue. That is another, but
Mm.
there is a lot of speculation. But I'll come to
Mm.
excessive risk that they're explaining about in a bit, which will, yeah. But yeah,
So the
actually,
only thing that they might have also looked at is they've used variational autoencoders, right?
yeah,
So in variational autoencoders, you are actually enforcing the representations, the latent space to be Gaussian
yeah.
because you're injecting the prior. So they could have also looked at like what can you do with the Gaussian
Mixture.
thing.
Yeah. They tried Gaussian mixture one instead of a plain Gaussian because, of course, there can be multiple smaller bumps. But I get what you mean, right? Like there can be some kind of like what kind of, I don't know, mean variance. What is the distance between two means and variance? What is the squeeness of like these whether it's tilting one way or the other. I think they have a lot more things to explore, but they are just assuming for the sake of
Yeah.
simplicity. Yeah. Because that will throw their paper into like 100 pages, right? I know.
Yeah.
Anyways, so there will be a little bit of theory. Okay. I'm going to skip like through this one quickly. I'm going to go through notation. As I just mentioned, they are assuming a simple, like the easiest one, which is a Gaussian mixture with no squeezy list, right? Like, and then just a mean and a variance matrix. Okay, this is for the sake of their theory, which is in their section 5. But like, if you're a math person, please feel free to read it. The other one, the true manifold dimension that they're assuming is they're assuming it based on the rank of the variance matrix, epsilon, sorry, yeah, being the variance matrix. And then the rank, if it is Q, then we are only selecting the top Q eigenvectors, which actually correspond to some kind of real variability. We have a classifier, we do an adversarial training. Remember that adversarial training is a min-max problem. Why is it a min-max problem? Is because we are trying to minimize the mu and epsilon such that the expected value of the maximum loss for all these adversarial examples is minimized. So the maximum losses when the adversarial examples are created, the average of these maximum losses should be minimized. Does that make sense? I think it makes sense, right? Okay, I'm going to keep moving then.
Yeah,
Then there are
it makes sense.
two types of manifold attacks. One is generative adversarial attacks, which we just looked at the algorithm one. They use a linear generative model like a PPCA for their theory work. And in the eigen one, they are using, oops, okay. And that's why their X adversarial is going to be looking like WZ plus delta Z. How delta Z is calculated, all of that. I'm not talking about all of that. Again, here, this one is because we are doing the singular value decomposition, eigenvalue decomposition. So we are going to use only the Q, the top Q, U representing eigenvalue, like eigenvalue matrix, and then projecting the delta Z, which is the variation, onto that to obtain the new sample X ADV. I know I'm just like skipping through a lot of details, but if you want to learn more details, there are more details there. But definitely I'm someone who would do that in a math class. So I'm not going to explain any math in here. There is a lot of math that I'm going to skip through, but they are definitely going to talk about excess risk. So the theorem one that in the paper suggests that the excess risk from generative AE for generative perturbations is nothing but theta of Q L inverse squared. Depending on the manifold dimension, this can be huge. So even though in adversarial training we try to ignore on manifold directions by a lot and only focus on off manifold directions, the excessive risk is still large because of their manifold dimension. That's what they said. They have done like a lot of math which I could not make any sense of. So I'm just assuming what they said is to be true. The other one is they have calculated the excess of risk, that means adversarial risk for the eigenspace perturbations, and they were able to find that that difference is going to be omega of the eigenvalue, the top eigenvalue or the top Q eigenvalues, and its inverse. So the higher those values are, the lower those values are, the higher that value is, right? Like the small eigenvalues would lead to the large vulnerability in case of an eigenspace perturbation. So based on their math, what they got is correct, which means the bottom eigenvalues are going to give large vulnerability on the adversarial attacks, not on the adversarial accuracy. So that's what they said. I'm just going to quote them and not explain them. But if you want to understand that, please go and read it. If you understand it, please get back to me and explain it to me. Anyways, so when the manifold dimension equals the ambient dimension, which is Q in our case, but the data actually lies on a low dimensional manifold, then what happens is, intuitively speaking, some of the eigenvalues are actually going to be basically zero. So in that case, the lambda values are going to be zero. And if you go like on the previous slide, you know that if, I don't know, 1 over 0 is again non-determinant, but I might do something which I was able to show in the meme and do some other calculation there. But based on those calculations and approximations that they made, they say that in such cases, the excess risk that is resulting from this assumption of a regular adversarial example will become infinity. So LADV minus L is equals to 1 over 0, which is infinity. This is because perturbations will explicitly, exploit the directions which has the zero variance. That means they're only going to go off the manifold into like from red to blue or whatever, right? If we assume the Swiss roll thingy. Regular attacks will always target these zero eigenvalue directions, which are off-manifold noise directions, where the classifier is least constrained. So they're only going to exploit these eigenvalues or eigenvectors, of course, because if you vary anything in the way in the eigenvector or eigenvalue directions which has variance, then you're most likely going to change the image by a lot, and it will be visually like change. Visually very different from the original image, and that's why they'll always exploit that. This one is kind of makes sense and is all correct, according to what we might think. But the first two, like the excess risk for eigenspace and the generative space, I don't know how do they get the Q, and for one case they get the omega, for the other case they get the epsilon. The theta. I am not too sure about that.
So, can you go back to the previous slide? So the first point, does that actually mean representation collapse? Like when you are training and
It will
some
be
of your
yeah, go ahead.
so is it like representation collapse? Because when you're training in so some of your latent space variables always map out to zero, let's say.
Yeah.
Then it's representation collapse. So
Yeah.
base so representation collapse in this case is good, because PGD attacks will always target zero eigenvalue directions and the images will become very different. Is that
I
is
think
that
that's the case. Yeah. So if we go back to where is this?
Yeah, because I think the objective is completely opposite in this case. So yeah, it might be helpful.
I think for example, when we are doing the GFGSM and GPGD attack, the accuracy is pretty low because now there is, as you just mentioned, we have no eigenvalues or eigenvectors that we are looking at, which has zero variability, or they are not explaining any variability in the data. So whatever we are attacking in these spaces is basically what we are supposed to be attacking, right? Like what is what will most likely be giving us some kind of variation within the data manifold instead of moving away. So what we are doing here is we are exploring adversarial examples that actually lie on the data manifold, which is kind of counterintuitive because we think that data manifolds look like this figure, but they might not look like this. They might look like
Yeah.
the
So
blue can be here as well. I don't know.
so
But
for example, let's say the data manifold was supposed to be A, but because of representation collapse, you got D.
Mhm.
You have D now. So you're saying that if the representation has collapsed in some way, um, then it is better for the model because it will be able to handle adversarial attacks better.
No, I'm not saying that. I'm saying it will not be able to attack them better. Does that make sense?
Uh, so the attacks won't work as well when you have representation collapse.
The attacks would work better because you have,
Would work better or wouldn't work
oh,
better.
wouldn't work better because now you're not exploring all those places where variability is zero by reducing it. Does that make sense?
Hmm.
Again, the assumption here is based on our data manifold and how we assume data manifold to look like, because nobody tries to see it in different. We can try to see it in like principal component A1 and 2, and that's all, or like principal component 3, like the how many 6 possible combinations or 9 possible combinations or whatever we can. But
Mhm.
apart from that, if we go higher up um, the chain of the number of dimensions, we are probably not looking at how these manifolds look like in terms of their composition, right? So their composition may not be looking like a simple this. Their composition might be
Mhm.
more complicated. And I have
Yeah.
one paper that I can share which explains that a little better. I don't know if I can pull that up right now, but it talks about same manifold having multiple decision boundaries. My assumption or speculation is that we are definitely looking at multiple decision boundaries on the same data manifold crisscrossing each other.
Mhm.
And that's why
Okay.
it's a little, if we assume this and keep this in mind, that the data manifold is probably filled with uniform composition for a given class at a given space and then moves to a different class altogether, that assumption is pretty basic or ignorant, I believe, given the results
Mhm.
that they're getting. Yeah, I know.
Okay.
I know it's a little complicated. I know the paper,
Yeah.
the topic, and everything is complicated, so I didn't want to complicate with the math and everything, but I
Mhm.
had to
Yeah.
mention
Yeah, yeah.
about the excess risk there anyways.
So excess risk means training error, right?
Yeah, yeah, like error or whatever. Yeah, same thing. Just a fancy way to call it that way, I think,
Yeah.
while you're doing some
Mhm.
theory.
Okay.
Um, okay. Um, I think this one is another interesting one. I know we are like too tired of this paper now. But what are they trying to show here, I believe, is how with the increase of the number of dimensions, the adversarial, like the accuracy, not accuracy, I believe. I don't know what this is. The average of generative attack directions is changing. I think it's average distance. How much distance do they have to travel in each of these directions is exponentially coming down early on as we increase the number of dimensions. So if there are
Mm.
close to one
Mm.
dimension, then in that one specific dimension where you can vary the data, you're going to vary that data so much over there. Whereas when you have multiple dimensions in which you can vary the data, you will vary the data in some random directions by only a small margin, is
Mm.
what they're trying to say. And that means as you move higher into dimensions, you're having more scope of exploitation, right, within the data manifold. Um, I think there is a sweet spot between adversarial training on the images versus adversarial training on the manifold, because on the manifold, we have a different kind of mathematics or different trend that we are looking at. But when we are in the input space, there is a different kind of trend that is happening altogether, right? Yeah, so there might be something if fundamentally different about the way data is represented or moves around in these two input spaces. And that's why I feel like that transformation that is happening from input space to latent space is kind of dramatic, because the math that is mathing in space A is not mathing in the space B at all. So anyways, I'll keep moving. I'm not going to go through this. It's basically again showing how um, as we increase the number of dimensions, what is happening with the amount of change in all those dimensions. Some of the observations from all these previous figures is the full adversarial distribution is difficult to characterize, and that's why, and that's because it's a min-max objective. And we know that min-max objectives are very like analytically hard to compute, and all of that. The second order statistics, which in our case is the eigenvalues, provides an effective way to describe adversarial distributions, especially in the latent space, but may not be providing us effective ways to analyze adversarial distributions in the input space. The last one is, I think, oh my God, why do I not have a last one here? Okay, adversarial training will primarily be fitting adversarial examples in low variance directions, which are all the small eigenvalues or off-manifold directions. Again, we are assuming that this adversarial training is only happening in the input space. The generative adversarial training is going to happen in the latent space. It's also primarily going to fit adversarial examples, but in high variance directions, which are the directions which have large eigenvalues. That means on-manifold directions. So as we jumped from one input space to the latent space, we are doing exactly the same thing with the two different kinds of adversarial trainings. And then lastly, because of this mismatch, adversarial training fails to learn from on-manifold adversarial examples in the case of input space. That means the 0.3, and that's why there is a huge robustness gap when we do adversarial training on input space. We are still not getting good accuracy or whatever, right? Anyways, coming to some future directions, I'm just going to enlist three of them because the paper has gone more than what I thought it would. We would be trying to characterize how adversarial distributions are, what do they look like, and control, how do we control them. We can design some norm-based on-manifold attacks similar to the attacks that they already have, the generative attack and the eigenspace attack, which has not been explored in the literature before. And this is like a 2024 paper, I think, or 25 paper. So it's pretty recent.
It's
And
2024. Wow, it's pretty recent.
yeah, it's pretty recent. So that's why I'm
Mm.
like, excited. Developing on-manifold adversarial training algorithms is also going to be really helpful. And why do I say that is helpful is because, as you can see here, these are giving really good results, but we are only looking at PGD 80, but we might also want to look at FGSM 80 or Kalini Wagner 80 or whatever others, and then see what that is going to look like. Oops, okay, what am I doing here? So that's all is what I have. I would probably like put in some questions that we had in this discussion come meeting, and I'll populate them here so that the slide deck is like a standalone thing. I hope you can search up the references for all the papers, attacks, defenses. I am not going to put them here. And in case if you don't think that this is the right paper to look at or tutorial, please shoot me an email or reach me out on LinkedIn. I'll be happy to help. Thanks so much.
Thank you, Ehsan.
Yeah, thank you for the interesting talk.
I know it went longer than was
Yeah,
expected.
it was good.
Very informative.
Yeah, this adversarial network, it was so interesting. Like, and what I feel is like the way how we do in active learning and in this, like we are selecting the data points, right, in the model decision boundary, but the concept is like fundamentally it is opposite. Like what you are doing is making the model more like prone to errors.
Yeah.
And in this case, we are trying to make it better.
Yeah.
Do you
Yeah.
find any relation like it can be?
In with regards to active learning, you mean?
Mm-hmm.
I think, yeah, if you look at adversarial training in one way, it's kind of an
Yeah.
active learning thing.
Mm-hmm.
But
Yeah, the
yeah, it's
way we do it like different,
yeah, the way.
fundamentally
Yeah.
is different, but the points like more uncertainty we are looking for is like
Mhm.
same. Yeah, but I think combining these two concepts would make the model more robust.
More robust. Yeah. Again, I think it's like very exploratory.
Yeah.
In the,
Interesting. Yeah.
yeah, in the adversarial space, there is so
Mm-hmm.
little that you can do. I mean, so little that has been done. So much more that you can
Yeah.
possibly do. Yeah.
Okay.
Sounds good. Okay.
Thank you.